Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about systems of three linear equations and three unknowns. To solve a system of linear equations, if you have two variables or unknowns, you need two equations. If you have three variables, you need three equations. If you have four variables, you need four equations, five, etc., etc., etc. During our last lesson, we worked with two variables, and we always had two equations to solve that system. Today we're going to talk about three variables, equations with three variables, and we're going to have three of those equations in order to solve the system. Now, if you want to work with four variables and four equations, we're not going to do it algebraically. In fact, that's beyond the scope of this course. But if you would like to look at how to do it, take a look at section 5.4 of your textbook for an introduction to matrices. Here we have a system of three equations and three unknowns. We can do this. Now it's just going to take more steps than what we were doing in our previous lesson. So what we're going to do first is examine all three equations to determine which variable to discard. Now, and at a number of times for the rest of the class, you will discover that there are multiple ways to reach the correct solution. And each of us probably tends to a favorite way of working things out. So that's why I'm going to have you work in breakout rooms, in groups, to practice solving these equations, because my favorite way to solve it may not be yours. And if you interact with someone else, you may find a better way for you to solve the equations. But anyways, here's my method. First, I'm going to label the equations that we have. I am doing this because we are not going to attempt to solve all three of these equations at once. Our method will take us through multiple steps, and we will generate new equations, which we will then combine to continue our solution process until we have a value for x, a value for y, and a value for z. So the numbers are an attempt on my part to help you keep track of where we are in the solution process. To get started, I need to look at the values of each of the variables to try to figure out which one might be easiest to get rid of first. As I am looking at this, I notice that the x's all have coefficients, the z's all have coefficients, and the y's, y doesn't have a written coefficient, it's just a 1. And -2 and 3 are rather small values. I'm going to get rid of y first. So I rewrite equation 1 and equation 2 so that I can now manipulate them. In equation 1, I have a positive 1y, and in equation 2, I have a negative 2y. So I'm going to choose to multiply the equation number 1 by 2. I'm multiplying both sides by 2. Ta-da! That's a technical math term. Now I can add the equations. When I perform that addition, I have a new equation. So I'm going to label it equation 4. Notice equation 4 has no y variable, it only has x and z. Now I return to my original list of equations and I choose two equations to add. I can choose 1 again, or I can choose 2 again, but I have to combine one of those with 3. So I'm going to choose to take equation number 1 and equation number 3 and add those. At this point, I have to remember that I got rid of my y value previously. I want to get rid of the y's in this pair of equations. So how can I do that? I have a positive 3y in equation number 3. If I had a negative 3y here, they would add to be 0, my y would disappear. So in order to do that, I am going to multiply equation 1 by a negative 3. This is where I'm combining two steps together. Equation number 3 does not change. Look, there's my positive 3y to go with my negative 3y in the top equation to make the sum of my y's 0, which makes them disappear. And at the same time, it gives us another equation that we can work with. Let me make some more room. Now we have equations 4 and 5. So we have two equations and two unknowns. Let's combine them. I think the easiest thing to do here would be to multiply 3z by -4 to get a -12z. I cannot just do that to one term. I have to multiply the entire equation by -4. And that leaves us with 82x equals 41. We are almost done. We just need to divide both sides by 82 so that we get the value of our first variable, x equals 1/2. Now we're going to work backwards. We have one variable. Let's put it into one of the equations that has two variables. But let's recognize something first. This is actually another equation. So let's label this equation 6. X equals 1/2 is equation 6. Now let's take 6 and substitute it into 4. So first we need to make some more room. So now we bring equation 4 down and we substitute 6 into it. Where once there was an x, we put a pair of parentheses, and inside that we put the value of x, 1/2. A little multiplication, and that becomes 5 plus 12z equals 13. Subtract 5 from both sides and divide by 12. Always remember to simplify your answer. Now look, we have found x equals 1/2. We have a value for x. We found z equals 2/3. We have a value for two of our variables. And by the way, let's call this equation 7 because it is an equation. Now we're going to substitute equation 6 and equation 7, in other words, the value for x and the value for z, into one of the original equations. Pick one. I picked equation 1, and I am going through the steps of solution. Pause the video if you need to take a moment to look at what I'm doing. I make a little more room, and here is my last step. Y equals -3. I now have all of my values. I have x equals, what does x equal? 1/2. Y equals -3, and z equals 2/3. But the way I would like for you to show this is writing it down as a coordinate triplet. There, if you must know, is a two-dimensional representation of that three-dimensional point on a graph. We are not going to be spending time graphing in 3 dimensions. So, are we done? The answer is no. By now you should know that there is one more step. Check your work. You have to check those 3 values in each of the 3 original equations. Pause the video and make sure you can get those 3 values to check in each of the 3 original equations. Well, that went well. No problems. Worked right through it, right? No, I control the editing software. I stopped multiple times to erase and fit that X in that I had just dropped, or insert the negative that I dropped. You will make mistakes with this method. There are multiple steps. Please stop at each line and double check what you have just done. Before I work through another example of solving 3 equations with 3 unknowns, let's talk a little bit about inconsistent systems and dependent systems. Which one might this system of equations be? Well, we have to do a little manipulation to figure this out. I think I'm going to go ahead before I try to add these, because if I do it right now, I'm not going to get rid of any variables. Before I add these, I'm going to multiply the second equation by -2. Because I have a 4x in the first equation, I'm going to multiply the second equation by -2, so I get a -4x there as the first term. And now I'll get rid of my x's. So then I have a 2y in the first equation and a positive 2y in the second equation. Look at that, I'll get rid of my y's also. So 3 in the first equation and -4 in the second equation. So let's go ahead and add now. My x's add to be 0, my y's add to be 0, so I just have 0 on that side and 1 on the other side, which is not true. This is an inconsistent system of equations. I didn't do it earlier, but I'm going to label our first equation, equation number 1, and our second equation, equation number 2. So let's graph those. Now that I've graphed them, you can see that what we have is two parallel lines. They never touch. So if you have a false statement, or if you have a graph that shows parallel lines, you have an inconsistent system. There is no solution. Let's look at a different example. Here's another system of equations. Two equations, two unknowns. If you work through it algebraically, you can get it to this form. And when you add those, it's always true. Why is that always true? Well, let's take a look at that. I've graphed the first equation, and now let me bring this second equation and put it in place. Yep, if my lines were a little bit more neatly drawn, you would see that those are actually the same line. Let me show you why. If I divide both sides of equation number 2 by the number 2, keeping everything balanced, that means I have to divide every term by 2, which is the first equation. The second equation is just the first equation multiplied by 2 and rearranged. So if you work with two equations and add them, and you get a statement that is always true, no matter what x and y are. In this case, it's always true because there are no x's and y's to mess it up. 0 equals 0. Or if you have a single line, you have a dependent system. But that's two equations in two unknowns. What happens when you get to three equations in three unknowns? I already showed you, or attempted to show you, how to graph a single point in 3 dimensions. What's it going to look like when we try to graph these equations in 3 dimensions? I'm going to rely on somebody else's diagrams. Before we move to 3 dimensions, please note that when you are graphing a line, you are graphing the set of all points that make the equation a true statement. And you're graphing in 2 dimensions, length and width, domain and range. But before we add a third dimension to that, we reorient our axes so that it's in effect taking a piece of paper that's upright and laying it down on a table. So we have the x and y axes here. Then we add our third coordinate axis, the z-axis. And our set of all points no longer is defined by a line, but the set of all points x, y, and z that make an equation true gives us a plane. So if we have 3 equations in 3 unknowns, let's say x, y, and z, and we graph all of those planes on one set of coordinate axes, then we have this, or maybe this, or possibly one of these 3. How do we interpret this? Diagram A there by itself, you see the one point that is the solution of 3 linear equations in 3 unknowns. In the next diagram there, diagram B, you see an intersection of 3 planes, in other words, 3 equations that has an infinite number of solutions, because any point along that line, which exists infinitely, is the solution for each of those 3 equations. And yet this is not a dependent system in the same way we had dependent systems with lines. A dependent system with a plane would be another plane that occupies the same space, or rather 3 planes that occupy the same space. Here we have 3 different planes, and yet they intersect to form an infinite line. The set of 3 diagrams gives examples of 3 different ways these planes could be oriented in relationship to each other, some of them intersecting, one of them with no intersections amongst the planes. They are all parallel. But in none of these cases is there one point or even one line that is part of each of those 3 planes. So all of those are examples of inconsistent systems. So let's move on to another example of algebraic solution of a system of 3 equations and 3 unknowns. Please remember that our first goal is to get to the point where we have 2 equations and 2 unknowns from the situation we have now. And take a close look at your system of equations. Number 2, the second equation here, already has only 2 unknowns, 2 variables. So we're just going to reserve number 2 and we'll use it later. Therefore, we're going to have to combine equation 1 and equation 3. Now we have to choose which variable to remove from our process. Which variable is going to add to be 0? Well, before I start analyzing these 2 equations, I need to look at the equation that has only 2 variables now. The equation I want to combine with that, to add with later, should have an x and a z in it, so obviously we have to get rid of y, and look at that. This one's going to be easy to get rid of. We can simply add them as written. So we'll get 3x, y's add to be 0, and plus 1z equals -3, +3 equals 0. We now have our fourth equation. So let's combine equation number 4 with equation 2. Our goal is now to reduce these 2 systems of equations to an equation, one equation with one unknown, and that unknown will then be defined as a value. So I'm just going to take this second equation and multiply the whole thing by -1 because that will get me where I want to go. I add the 2 equations to get 2x equals -2, divide both sides by 2, and get x equals -1. I have my first variable. I'm going to put it in a box that's dotted because I need to check that to make sure I've done it correctly. I'll check at the end. And now I'm going to put that equation, x equals -1, that value for x, into one of the equations that I have that has only 2 variables. I'm going to choose number 2 again because, hey, it's easy. Let's see what happens. If for number 2 I put -1 in for x, so there's my x, put in -1, plus z equals 2, so then I add 1 to both sides and get z equals 3. There I have found my second variable. Now I have to put both of those values for the variables into one of the original equations that has an x, a y, and a z. So I'm going to go back into equation 1. My x value is -1. My y value, I don't know yet. And my z value, I am subtracting whatever z is. Z is 3, and this should equal -3. Combining like terms, I get -4 plus y equals -3. Adding 4 to both sides, I get y equals 1. Those are my preliminary findings. They are not confirmed until I check each equation. Equation 1, equation 2, and equation 3, with my values for each of the variables inserted. Now I may confidently say that I have found the solution of this system of equations, the solution being -1, 1, 3, that point. During class, you will have the opportunity to get into groups in breakout rooms and work some examples of systems of 3 equations in 3 unknowns, and we will talk a little bit about the application of such systems. So I'll see you then.